All right, guys, let's think about kcat a little bit more, right? So in the case of the simple, the Cayless-Minton scheme, right, or the Briggs-Haldane mechanism, more accurately, the meaning of kcat is fairly plain, like I pointed out before. In this case, kcat is simply equal to K2, that unimolecular rate constant at which one does chemistry, right? But in the case of this more complex trypsin-like mechanism, kcat's a little more complex, right? Kcat is a combination of K2 and K3, specifically K2 times K3 divided by K2 plus K3, right? So in the case of this more complex mechanism, kcat is a function of all the first order unimolecular rate constants that describe the process. And that turns out to be a general observation for these steady state kinetic mechanisms derived under the assumptions that we applied to get us to that Briggs-Haldane Michaelis-Menten mechanism. That for these more complex reactions, something like this is always going to be the case. That kcat is no longer a simple single rate constant. It's a combination of all the unimolecular rate constants on the forward reaction pathway, right? Okay, and only if one of those rate constants is significantly much smaller than all the rest can kcat be assigned to any single step. And for these more complex mechanisms, it's a combination of all these forward rate constants. But if you look at something, it's still a unimolecular rate constant, right? Because if you look at the units here, what's that? K2 times, if you look at this, K2 times K3, that's going to be like, second to the second squared. K2 plus K3, that's going to be, seconds to the -1, which means the units of kcat are still per second, right? Or per minute or per hour, whatever. That, again, is a general observation of the algebraic form of these kcat constants, which you can also then think about as sort of a K observed, if you want to think about it that way. Where kcat is equivalent to sort of an overall observed unimolecular rate constant for the rate at which the enzyme turns substrate into product. Under certain circumstances, you can, like I said, assign it to a single step. So for example, if we had a mechanism that maybe was complex in the same way as the chymotrypsin mechanism, this isn't true, but let's say we had something that had similar design, but where, say, K3 was much smaller than K2, right? Under this circumstance, what would kcat be equal to, right? If you think about that, you'd have K2, K3 over K2 plus K3. If K3 was much smaller than K2, then in the denominator here, K3 wouldn't matter, right? Because it'd be dominated by K2. And now in the numerator, okay, those would cancel out, which means under that set of circumstances, kcat is just equal to K3. This is a situation where it's a special term where K3, even though we would have multiple steps in this multi-step mechanism, in this particular case, be saying that K3 has now become rate limiting. Because it is a unimolecular forward rate constant that is much smaller than all the rest of the unimolecular rate constants. It therefore dominates the kinetic behavior, and it kind of, in the limit, becomes the only one that matters. But when that's not true, right, when you don't have any single step that's rate limiting, you can no longer then assign kcat to any individual step. Under those circumstances, it's a combination of this sort of form of all the first order rate constants, right? But as I said, it remains a unimolecular rate constant, right? Because this is always the basic form one would get under the assumptions of steady state enzyme kinetics, right? Okay. Another couple things to think about with kcat. another way to think about it is that even under situations where it's a combination of the underlying unimolecular forward rate constants, it can't be any greater, right, than any true first order rate constant in the forward reaction pathway, right? The kcat can never be any larger than that, right? So you can think about kcat as sort of setting a lower bound on the rate at which chemistry can happen. Now, it can be a combination of multiple steps, like in the case of the chymotrypsin mechanism. We've got our amide splitting chemistry happening there at step 2, and then we have our sort of, water-induced regeneration of free enzyme. For chymotrypsin, they both contribute because neither one, even though K2, for some of these families of enzymes, K2 is so dominant that it effectively becomes kcat. For others, K2 and K3, as I've drawn here, both contribute to kcat, right? Okay. So another way to think about, or another sort of general statement about kcat is it's a function of all the properties of the enzyme substrate complex, any enzyme intermediate states that exist in enzyme product, right? kcat is sort of determined by all the features of those intermediate states as they progress down the forward reaction pathway. And under steady state assumptions, they will always generate an expression for kcat that is a function of the underlying unimolecular rate constants, right? Okay, so another way to think about kcat, or it sometimes gets another name, like I said, let's just leave that up there. kcat is also known as the turnover number for an enzyme. Right? That's another general way in which kcat is sort of referred to. And if you think about the idea that, even with these more complex combinations of unimolecular rate constants, it's still an overall observed unimolecular rate constant that makes some sense, right? So if you had an enzyme as complex as this chymotrypsin mechanism, and I were to tell you that, well, kcat, in that case, I'm just making this up, it's approximately right for these enzymes, is 1,000 per second. What does that mean to you? When you think about it, all the discussion we just had. kcat is 1,000 per second. All right, you think about that good turnover number. Well, what that tells you then is the maximum number of substrate molecules that the enzyme can turn into product, right, per unit time, right? I would say, in this case, per second, right? So there's an interesting analogous way to think about kcat. If you think about the way we talked about rate constants and time constants with respect to simple exponential decays, you can do something similar here. What we think about if I took the inverse of kcat. Remember, no matter the complexity, if you adhere to initial rate steady state conditions, you're still going to have an apparent first order rate constant for production of product. If I took the inverse of that, right, in the case of, say, this example down here of 1,000 per second, what would that be, right? Well, you'd end up with something kind of like a time constant that in this case would be 1 times 10 to the minus 3 seconds. So what does that mean? Sorry about that. I keep having my iPad is dropping the screen share. So again, if you think about taking the inverse of kcat, right, and you get this number that now is in units of time instead of inverse time, what does that mean? Well, that tells you the average amount of time it takes to convert one molecule of S into P, right? So in the case of an enzyme that had a turnover number of 1,000 per second, so it could do 1,000 molecules essentially per second, then the average amount of time it takes to do one molecule would be a millisecond, right? Okay, next video, we're going to think about Km.